up. Getting back to this, in the retransmit problem, what happens if the ACK or NAC is corrupted? Just what we went through. Now there is much more detailed, much more involved implementation that Nathaniel walked us through, but at the simplest, you just add a sequence number to the packets. Right? So we get down here, we get the NIC back, we send an ACK saying, I don't know what you sent, then we get an ACK. If there's a sequence number in every packet that's being transmitted, we now know, we get this ACK back, if the server side appropriately constructed the ACK, it sends an ACK back with the sequence number that it is acknowledging. So now we get down here, we say, oh, the ACK is for the NAC. Okay, you got that. And now I get this next NAC. Even if there's no sequence number in there, I can determine what is being NAC because I've already, if you will, canceled out the one sequence number that had an outstanding missing NAC or ACK, right? But if I add a sequence number to every packet, it doesn't even have to be involved. In our very simple case, we can just use two numbers, 0 and 1, right? Depending upon the sequence number I get, I can tell which packet that I sent is being acknowledged. Simple stuff, right? And what is that? One thing we haven't talked about is, as a sender, I have to hold on to the packet I sent until I get something back, right? If I get a NAC back, I better still have that packet in the buffer. I don't want to go up to the application layer and say, what was that you told me to send again? But if I keep it within a buffer, I get an ACK back, I can flush that buffer. Don't need it, discard the packet, wait for the next one. So, RDP 2.1, the sender handles garbled ACKs and NACKs. And how do we do that? Because we start implementing not only the checksum, but also sequence number. And at the very top, you'll see that we're waiting for the data. We get the request down from the application layer. We generate the packet for the send packet, right? And that first number in there, the 0, that's our sequence. Why am I starting with 0 instead of some other number? Could the 0 be 7? Morning. This is a trick question. Can that sequence number be 7? Can it be 2,417,000?
Probably.
What?
Could be. Is it?
The correct answer is could be. What would have to be in place for that to be okay? In the application architecture, I've defined what the range of sequence numbers I'm going to use is. And if I decide it's going to start with, I forget what I said, 2,417,000 or whatever that is, then so be it. Not only do I know about it as a sender, but I also know about it as a receiver. So the sequence number can be anything that's generally agreed upon. It's easiest to start with, actually not even a 0, to start with 1. You're using 0 and 1 because it's, in effect, it's on and off. And it's a convenient convention for discussion. But as long as both sides know what the very first sequence number has to be, That sequence number can be any number, just so long as the very first packet that's sent has that number in it, and every packet thereafter we increment by 1. And then eventually at the end of the range, we wrap around again. That's how it works. That's how every sequence numbering scheme for every protocol works. I'm leaking. Okay? Hypothetical here. For reliable data transport, we've added checksums. So a checksum allows us to understand at the receiving end almost exactly what the sending end thought they sent. We've added a sequence number, so at the receiving end we can almost understand without any doubt, without any error, where we are in the transmission sequence. What would you do for your application architecture if you wanted to foil a man-in-the-middle attack? Given that the man-in-the-middle will be able to see or figure out how you're creating your checksums and how the sequence number range progression is working. This is a trick question, but it's a pretty difficult one. You can't figure it out, it's because your instructor is mean and you spent too many years trying to figure this stuff out and battling bad guys. How about you start to say something? You want to finish?
Sending some random numbers. Like
You could do that, but we just talked about it about 2 minutes ago. In what kind of architecture? Application architecture or network architecture?
Network. No.
In your application architecture,
Yeah.
if you want to use what you suggested, which is periodic injection of some random sequence number into the stream, you codify that, you formalize that in your architecture, right? So that both ends understand, right? The last sequence number I got was 4, and all of a sudden I receive a packet with a sequence number of 8 billion. On the receiver end of my application, it's probably good if I don't freak out, right? So that's one thing you can do. Another thing you can do is for checksums, you can programmatically in your architecture change the methods you use to generate your checksums on a regular basis. That'll foil a man-in-the-middle attack. You can also, in your application architecture, you can specify that periodically you change not only how you generate your sequence numbers, but how you increment them. And what, if you do this in your application architecture, what would prevent you from somewhere 5 minutes into the transmission between server and client, what would prevent you from deciding that you were going to increment the sequence numbers by 3 instead of by 1? Absolutely nothing. Both sides understand that. They know that after 7.5 minutes, sequence numbers will now be incremented by 3 for the next 2 minutes and 45 seconds. All that needs to be understood is that the timer started when the first packet was sent. And how do we know what time that was? It's in the header information we received, right? One of the other things that's in the header is a timestamp. So you can do all these things. These are some ideas. Keep these in mind. This is without exposing too much. If I had worked on some secret communications protocols being used by the United States Department of Defense, this might have been one of the schemes that we used to foil network attacks. Because two endpoints do something like this, and you have some nefarious bad guy in the middle who's intercepting communications and hoping to decode your secrets, and all of a sudden sequence numbers are jumping by 5 at a time. And you set up the time frame or the value that dictates how long you do this change in sequence numbers to a small enough value that the man in the middle can't reliably determine whether it's an error or whether it's a programmatic change. It's going to now become very difficult for that man in the middle to decide whether or not he's missing packets or he's indeed getting the entire data stream. So when we go through these exercises, think about these sorts of things. You can't go wrong. Well, that's not entirely true, but if you decide in your application architecture you're going to employ some of these strange methods to secure your communications, as long as you decided and you formalized it in your application architecture, you can't go wrong. The worst that can happen is you make it too easy for the man in the middle to figure out. All right, enough. So, how do we handle garbled acts and knacks? We've already gone through that. Any questions about it? I mean, it's fairly simple, right? Here we're showing, we come down, we set it to 0, we do the send. The receiving side is waiting for the packet. Meanwhile, the state transition from the sending side is to await. We're waiting for either a knack or a knack for sequence number 0, because that's what we just sent. And you'll see there the state transitions depending upon what we get back. All right? Here we, on the sending side, oh wait a minute, this is the receiver logic. The other was the sender logic. Here's the receiver logic. Right? We're just waiting to get something. If this is first time through, from an architectural perspective, we know what sequence number is going to be the very first sequence number that we're going to expect, right? And we just know it's programmatic. It was formalized in the architecture. Thereafter, depending upon what the architecture is, we're sitting and waiting for the next sequence number in the progression. Okay. We can go through all this stuff, but this is just a mirror image at the receiver side. Oops. Why didn't it go back to sender? Oh, because I'm going the wrong way. Okay. we are not going to get, we're only a third of the way through this part of the chapter. At the end of today, is it going to, you think, be valuable for me to give you all the slides for this entire part of the chapter, which is just reliable data transport? So that you can look at these diagrams? Is that going to help? Okay. Don't let me forget. Okay. All right. So the receiver end, this is how we handle garbled ACKs and NACKs. And at the receiver end, the problem is I may get a NACK back to something that I have no idea what it's a NACK to. So I implement sequence numbers, now I know. Now, with the sequence number included in this packet, now I can say up here, oh, that's an acknowledgement that the packet was received, but it was bad. So here, I can acknowledge, I have to acknowledge by architecture, I have to acknowledge that I received this packet okay. So if this is sequence number 1, then this is going to be an acknowledgement to sequence number 1. And if I'm using 0 and 1, what's the sequence number going to be here?
0?
Correct. Down here, this is going to be, I resend the sequence, I resend the NACK for sequence number 0. And what's sequence number 0? Sequence number 0 is way the heck up here. Right? But now, getting a garbled ACK or NACK isn't a problem. Although we're lying. Because if we're only using 0 and 1, if we get a transient bit error, it changes the sequence number. Now we got a problem. Right? But hopefully, if the sequence number gets clobbered, at least the checksum agrees. Well, the checksum reflects the fact that it was the sequence number. Typically, you generate the checksum. The checksum is representative of the data only, the payload. And so if the checksums agree, you know your payload is okay. What got clobbered is something in the header. All right. So, discussion. Sequence number is added to the packet on the sender side. In this case, we're saying 2 sequence numbers will suffice. Why? Data transfer is unidirectional. There's only ever, well, as far as the data is concerned, the data is only flowing one way. From sender to receiver. Information flows back the other way in the form of ACKs or NACKs, but there's no data per se. Does that make sense? So we can use 0s and 1s, and we're going to pretend like transient bit errors will never happen in a sequence number. Okay? The sender, once they've sent, they've got to check, right? They send. The functional state machine changes state to what?
Wait.
The FSM changes state to await. It needs to know whether the data arrived at the other side and whether it arrived in good shape. And that's going to be reflected in either an ACK or a NACK. Okay? But we've just doubled the number of states that the machine can be in. So from send to receive, it now goes to send or receive, good or bad. And also which packet. At the receiver end, you've got to check, we haven't even talked about it yet, but we've also got to check about duplicates. Okay? Is it possible that as the receiver, I could receive duplicate packets? It is conceivable, it's theoretically possible that a transient bit error changed an ACK to a NAC. And if the sender receives a NAC, so far in our architecture, its response is what? It resends, right? You resend the packet. Right? Make sense? So now it resends the packet, but it's resending the packet in error because there was a bit error on the ACK that changed it to a NAC. And now the receiver gets the same packet twice. So we want to make sure that that receiver end can also handle, understand, and take action on duplicate packets. And how do we know that? This is a trick question. How do we know if we got a duplicate? It could be checksum. You got two packets with the same checksum value. It could be you got two packets with the same sequence number. What happens if we receive a packet with the same sequence number, but the checksum is different? Is that a duplicate? It's a very tricky question. The answer is, if we receive a packet that has a duplicate sequence number, but the checksums are different, logically it is a duplicate packet. Physically, in reality, we've encountered a bit error. Right? It's a duplicate, but there's been a bit error. Which packet are we going to keep? Neither one. We have no idea. We think it's a duplicate because the sequence number is the same, but I've got two different checksum values. So which packet contains valid data? Not a clue. So what does our response have to be? Here's the answer. From the receiver side now, I've got a real problem. I don't know which packet is good. I have to keep both packets. I have to NAC that sequence number, and then I have to wait for the arrival of a packet with that same sequence number again. So now I've got three, all with the same sequence number. And now I've got to recompute the checksum, compare the checksums, and whichever packet the new one agrees with is the one that I keep as being valid and I pitch the other. Does that make sense? Here's some time. Should I diagram that? Do you want to diagram that?
Yes.
Okay. Okay, I'm at the receiver side. I get one packet comes in. It's got, and we're going to use the format sequence number checksum. So the first packet comes in, it's got sequence number 0, it's got checksum 8. Okay? Assuming that there's been some problem, there's some, not even failure, but just some unexpected logic occurring at the sender side, I receive another packet, and it's got sequence number 0, and it's got checksum 7. Which one's good? There's no telling, right? Who the heck knows? Right? Got no idea. So we've got to send an ACK back with sequence number 0. Have I thrown either one of these away? Typically, that's what happens if you get a duplicate packet. If I get a packet, I look, the sequence numbers are the same, I recompute the checksums agree, I throw away the oldest one. Gone. That's how you handle a duplicate. In this case, I've got no clue, right? So I've had to NAC sequence 0. I've got no idea what you're doing. Resend it again. Assuming that we're not exhausting the retry logic, as Nathaniel pointed out, at the sender side. Sender's going to resend it, and now I get in 0, 7. At this point, the only option I have as the receiver is to say, okay, this is what is received in response to my last NAC. Therefore, this is what the sender intends in all probability, unless there's been some error. However, if I compare that with the two I already have about which I am in doubt, about which I have no clue, I see that these two agree. Therefore, if these two agree, what happened here?
Let's go.
You
chuck it away.
Well, we check it, but
Yeah.
this is the one that had the error, right? In fact, I will tell you that this had 2 transient bit errors. 3 transient bit errors. Change the 7 to an 8. Okay, makes sense? So I know these two agree. Therefore, this gives me at least about a 70% probability that I have the right data, because 2 out of the 3 are correct. It's actually 67%. Actually, it's 6.6. So I know I can pitch these, but I can assume that this one's good because it agrees with at least one of the ones I had received already. Okay? Does this help? All right. So, the receiver in, check to see if it's a duplicate. If it is a duplicate, figure out whether or not it's worth keeping or whether it's worth pitching. And then send an ACK back. At this point in the logic, I received that one, I send an ACK, but before that ACK can arrive at the other side, the sender's already resent, gets here. Now at the receiver side, I gotta throw up my hands there. Ignore, hopefully, my last ACK. You got no idea what's going on. Now I send the NAC to sequence number 0. This assumes that at the other end, the sender's going to get an ACK to a packet that it just received an ACK to, and the sender's going to be smart enough to say, okay, something goofy's going on. Let's try a resend and see what happens. Right? But now, this is how I deal with duplicates that differ because of the checksums. Now suppose I received 2 packets, the sequence numbers are different, but the checksums are the same. Is that a duplicate? Sequence numbers are different. Assume I've ACKed appropriately the first packet I received. So I got 0, I got 0, 7, send an ACK. I get 1, 7 using this convention I've got here. Is sequence number 1 a duplicate or not? Again, this is a very tricky question. Well, it's semi-tricky. Is it a duplicate or not? Your first impulse is to say yes and you'd be wrong. Is it possible, is it conceivable that packets with different sequence numbers can contain the very same data? Absolutely. In your browser, what happens when you hit the refresh button? You ask for a resend of the exact same thing, right? So, we've narrowed the problem down. At the receiver end, we don't have to worry so much about packets containing the exact same data but having different sequence numbers. We just have to worry about packets that have the same sequence number but have different data. So when we implement our reliable data transport state machine, that better be something we keep in mind, right? Okay. RDT 2.0, a NAC-free protocol. How about, I don't want to get too deep into this, and this is about another half a dozen slides, and we're running out of time. So let's stop here. You can look at the sun. While I make a note to myself. And are there any questions? Are there any points of confusion? I want you to be writing your server-client pair. Do we have anything from Ray about the AWS yet?
Yeah, I'm trying now.
Okay.
Yeah.
So first thing you're going to do is going to be your first is just going to be the client server pair. And make sure that that works. And remember, the first implementation, this will send, the client will send something in lowercase, and the server will respond with that having been folded to uppercase. Right? And then after you do that, then you're going to use the same client server, but now you're going to change it to do or add RDT 1.0, 1.1, 1.2 if you want to implement the logic that is a little more detailed in discovering and dealing with duplicates. Right? And that is not necessarily for Tuesday, because, see, this gosh darn it, because we have no idea whether you're going to be able to get the state machines up and, the virtual machines up and running at Amazon, and whether you're going to be able to get all of it done. But this is just where you should be. Think about this is how far you want to get in the coding that you're going to be doing. The coding is all in the it's in the book, and we also, I sent the Java and also, I think Python is the other language used for the examples. Very simple stuff, you know, at most maybe 10 lines of code or something. In your